So this is a short video on electromagnetic radiation. Why do we care about it? On the AP exam, we can think about electromagnetic radiation as a great tool to help inspect atoms and molecules. Again, here's our equations where we'd like to realize that since the speed of light is a constant for all electromagnetic radiation, which we can call light, of course only a small segment of the electromagnetic spectrum is visible light, but the wavelength of light and frequency are inversely proportional. Because the speed of light is a constant, they are inversely proportional. Whereas you can see that energy is directly proportional to frequency. So it's worth noting, here's an image of wavelengths that are longer and longer. Long wavelengths correspond with low frequency, low energy, whereas short wavelengths correspond with high frequency and high energy. Well aware of Roy G. Biv, which, it doesn't really matter which way the spectrum will be written. I've seen it both ways in the AP exam, where high energy and high frequency are on the left, or high energy and high frequency are on the right. As in this spectrum, this would be high energy, this would be lower energy. So you'll see it both ways. We'll look at some questions. This is obviously not an AP question, but I ask it to get us a little bit familiar with what these terms mean so we can be comfortable depending on what question will come down. So you're asked to look at the following selections and decide which are true. Pause, make a decision. And so this top image has a shorter wavelength, which indeed means higher energy. This bottom wave has a longer wavelength. And so that makes number 2, of course, false. The top wave has a higher frequency, which corresponds with a higher energy and a shorter wavelength. Amplitude is not likely to be on the AP exam. I throw it in for when you're headed to physics. Amplitude is the height, and these are obviously equal. And so how bright a light is will be the height of a wave. We haven't seen that on the AP exam. If the top were red light, the bottom couldn't be blue light. It would have to be infrared or microwaves. And 6 is making number 5 false. 6 is obviously false because we learned that c, the speed of light, is a constant for all light. And yes, indeed, if the top were ultraviolet, higher energy, the bottom with longer wavelength could be infrared, which would be lower energy. Which wavelength below out of those listed has the lowest energy? This obviously would not be an AP question, but just to get us familiar with the energy involved with the various types of electromagnetic radiation. The lowest energy would be microwaves. Again, one more time, microwaves, low energy, low frequency, long wavelength. And X-rays at the other end of the spectrum, high energy, high frequency, short wavelength. Now, we've talked already about PES. And so which measurements could be used, which radiation below could be used for PES, as well as analysis of bond lengths and atomic arrangement in crystal structures. So that would be X-rays. X-rays have enough energy. X-rays, of course, are high energy, and that is enough energy to remove all of the electrons, which is what's needed for PES. X-rays are also used to measure bond lengths because just like your bones, the nuclei of atoms shows up as more dense on an X-ray image, and we can tell how far apart nuclei are of adjoining nearby atoms, and we were able to tell bond length as well as arrangement. So which radiation below could be used to analyze concentration? Likely you did some lab work with that. And sure enough, visible light. Turns out that ultraviolet could also be used. That wasn't an option. You may remember using the spectrophotometer, the visible spectrophotometer, to analyze a blue solution or a Gatorade type solution, as well as some work with crystal violet when we were in kinetics. So what's going on here? What's with these electronic transitions? Suppose we have an electron here in a third energy level of an atom. As energy comes in, that electron will bounce out, it pops back down, and energy is released in the form of visible light. Radiation below could be used to study vibrational motion of molecules, i.e. the bending and stretching of bonds. Clearly it's not going to be these high energy, so you're left to deciding between these two. Let's take a look. The answer is infrared. Infrared is enough energy to cause stretching of molecules, bending of the bonds, changing the bond angle in molecules, whereas lower energy, microwave, is simply the movement of molecules, whether they're twirling around, moving along, twisting in this manner or that manner. And you know that from heating water in a microwave. It so happens that water molecules in particular are very susceptible to the same frequency as the microwaves are, and that's why we use it to heat our foods. And lastly, this summary